Our next speaker has lived on 3 continents. I want to know what 3. So when you come down, you have to tell us. Please welcome Kim.
Hello, everybody. Thank you for coming back for the second day. My name is Kim-Eng Ky. I am a data scientist with the Federal Reserve Bank of Minneapolis, and I am here today to talk to you about a causal inference method that we use to evaluate the Minneapolis 2040 comprehensive plan. A little bit different than the other talks you've seen so far, but I hope it's interesting to you all. Before I go any further, I want to emphasize that the views and opinions expressed today are mine and mine only, and not necessarily those of the Federal Reserve Bank of Minneapolis or the Federal Reserve System. So why are we doing this? So this is a partnership between the city of Minneapolis and the Federal Reserve Bank of Minneapolis. In 2018, I believe, the city of Minneapolis passed the 2040 comprehensive plan that went into effect in late 2019. And so for our purpose, when we talk about post-treatment, pre-treatment, when I say post-treatment, I really mean 2020 and later, and pre-treatment is 2019 and earlier. The goal of the plan was that by 2040, quality housing throughout the city of Minneapolis was affordable and accessible to all Minneapolis residents, regardless of their race, income, or anything else. And with the adoption of this plan, Minneapolis became the first major U.S. city to eliminate zoning regulations that ban duplexes and triplexes in what used to be single-family detached homes only zoning. So how did we do this? There are three topic areas of interest. So the adoption of the plan, what we wanted to see was that there would be more housing, more affordable housing, and also more equitable housing. There is no one indicator, metric, or measure that could capture all these 3 topic areas. And so what we ended up doing was to develop 10 different indicators that capture different aspects of these 3 topic areas. For each of those 10 indicators, we estimate the treatment effect of the plan using the synthetic control method, or sometimes I'll refer to it as SEM. The SEM doesn't really, at least with the app package that we use to implement this, it didn't give us a way to assess statistical significance. And so we went one step further and developed or adopt a permutation test to assess statistical significance. So just a way to calculate p-values so that you can say whether or not that treatment effect is, significant or not. All right. So before going into talking about the what the methodology is and how to implement it, why do we even consider synthetic control? Traditionally, what people have done in the past is maybe pick a similar city. So we're talking about Minneapolis. You might be tempted to say, why don't we just compare it to St. Paul? It's close enough, very similar housing market, and it's like maybe it's a good control city for Minneapolis. But maybe the population makeup is different. Culturally, it could be different. So there are so many things that could go wrong with just picking one city. And then you can say, why not pick 5 cities? Maybe look at Chicago or some other cities that are closer, may have similar economy and the housing market and all of that. But then you have to decide, do you want to take simple average or weighted average? And if you do weighted average, what weights should you give to each of the city that you pick? And how do you know that they actually follow the same patterns that would give you what we call the counterfactual, which is the what the outcome would have been had the plan not been implemented. And so with synthetic control, or SEM, what it allows us to do is to systematically select the comparison groups, and also gives us their weight, so we don't have to make that subjective judgment, which could be different depending on who makes the decision, right? And then most importantly, because it weighs the control groups to better match the treatment group before the intervention. So this is 2019 and earlier in our study. It accounts for the effects of the confounders changing over time. So, we only have like one big confounder I can think of right now is probably the COVID pandemic, like, just a tiny thing that happens to start at around the same time as the start of the implementation of this plan. But the pandemic affected or still affects every city in the U.S. And so, yes, maybe the effects may be a little bit different across different cities or very different, but we can assume that it affects everybody. So on average, it should not affect our treatment effect estimation that much. But what about events that may only affect the treatment unit? So in this case, Minneapolis. So I don't know if you all have heard, but in summer 2020, there was the murder of George Floyd, the civil unrest that all started in Minneapolis. So it confounds with our treatment a little bit, but at this point, we're hoping that what we find is still valid. That's not really anything we can do. Like we can distinguish that effect from the plan. All right, and of course, as a statistician, I have to give you the assumptions before going into talking about the methodology. So there are three assumptions that I want to point out here. So when you choose your control units, or sometimes I'll refer to them as donor cities, they cannot have similar policy change. And the policy of interest, so in this case, the adoption of the plan cannot affect the outcome in the control cities. And so no spillover effects. So we want it to be clean. And then, SEM, what it gives us is it calculates the weight of the donor cities. So what it really gives us is the weighted average of the donor cities that then make up the control series, or like the path of what Minneapolis could have been had the plan not been implemented. And so one of the assumptions is that counterfactual outcome can be approximated by a fixed combination of those donor cities. Now, with all of that out of the way, let's talk about what SEM really is. I'm giving like very conceptual overview of the methodology. I have a link in the slide that links to like much more technical description of the methodology, all of the mathematical notations that I know you all love, but I decided to skip for today. So first, you want to identify predictors of the outcome variables. So in this case, our outcome variables, there are 10 of them, right? Like I mentioned we picked 10 different indicators. And what we didn't want to do is to customize the process or the procedures for each indicator. We wanted it to be general enough that we could apply to all 10 indicators. So we follow the same one. And so then, trying to like stay away from like choosing something that gives us a good outcome versus like something more general enough so that like we're not p-hacking our way into like a good outcome. And so in our project, we picked these predictors. So we have total population, home ownership rate, median housing cost, median household income. And because again, this is still a time series, we're looking at data over time. We want to take into account past values as well. But you also don't want to like use every single pre-treatment value to like fit your model. And so we compromise and use odd year lag values of the outcome as predictors. And then the next thing is identify potential control units or the donor cities. As I mentioned earlier, there are a few assumptions that we have to meet. And so when we picked donor cities, those came into our decisions on like what cities to include as well. And Minneapolis, I should know this, but I think Minneapolis has the population of about like between 300,000 to 400,000 people, I believe. And so it's like we pick a range of population of cities to be included, to like be somewhat similar to Minneapolis. And so we chose 150,000 to 2 million. Those cities cannot have any policy in effect at around the same time. Portland, Oregon, and then like a lot of cities in California actually like looked into like similar policy change in terms of zoning, and so we excluded all of them. Donor cities also cannot have any spillover effects. So St. Paul, we're not included. We're not including them. We're not including St. Paul in our donor city pool. And then the other two is just, with like working with census data, it's like they have to be a census place so that we can pull the data. And then it's like the cities have to be like one of the main cities. Like it can't just be like something random. Yeah. And then once we have the predictors and the donor cities, we can calculate the predictor weights. So these are the weights. These are the weights that go into the next optimization problem to give us the control city weights. So this is not like the weights that we are using to estimate to get the weighted average of the control cities, but it's important because it goes into that optimization problem. There are two ways that are implemented in the package that we use that I'm going to talk about in a little bit. So one is to give it equal weight. So if we have 10 predictors, each one would get 1/10. And then the other one is regression-based weights. So this is where all of the data, like the predictors data and the outcome data over time, all of the pre-treatment data get put into like a regression model, and then it spits out the weight for each of the predictors. Again, like all of the technical detail on this is in like the technical appendix that I'll share the link to later. And then finally, it's like once you have the predictor weights, you can put them into the optimization problem, and then it's like what it does is it minimizes the root mean squared error. You try to minimize the root mean squared prediction error, and it's like whichever method, whichever set of predictor weights that gives you the least RMSE, that and then that will give you the final control city weights that then goes into your weighted average to get your synthetic control series or the counterfactual. I'm skipping over on a lot of details. There's so much more detail in the technical appendix, but yeah, so it's like, so these are kind of like the steps that we can do to implement this method. And then once we get the weights, we can calculate the counterfactual post-treatment. And then next thing is we do the statistical assessing the statistical significance. So calculating p-value, we all love p-value, right? Like it has to be below 0.05. I don't believe that, but yeah. But we have to pick a cutoff. We actually use 0.1 in our project, but yeah. So I'm running out of time, so I'm going to go through this pretty quickly. So to calculate p-value, what you want to do is running the same SEM on all your control cities, and then calculate the RMSE post-treatment to pre-treatment. So if SEM fits your data well, so this would be like for the control cities, there's no plan in effect, so they should fit pretty well. And so the ratio, the RMSE, the post to pre-treatment RMSE ratio should be pretty small. For Minneapolis, if there is an effect, the RMSE ratio should be larger because now, right, like it fits well in the pre-treatment, but it does not fit well post-treatment. That means there's an impact of the plan. And so then to get to the p-value, in a way you can think of it as like ranking each of the control cities and Minneapolis. So we have 126 control cities that met the criteria I talked about, and then Minneapolis, so 127. And let's say Minneapolis has the 10th largest RMSE ratio of all the cities. That would give us a p-value of 10 divided by 127, which is around 0.08. So that's how we did our statistical significance assessment. So now the implementation. So this is one of the 10 indicators that we study. So this is housing cost burden among extremely low income renting households. Cost burden means you spend 30% or more of your household income on housing expense, and extremely low income households are households that earn 30% or less of the area median income. Just a little plot to show you, like this is the data for Minneapolis that we have. The package that we use to implement SEM is Synth. So Synth implements synthetic control methods for comparative case studies designed to estimate the causal effects of policy interventions and other events of interest. You can just do the install.packages and then like load using library, just like any other app packages that you use. And then, so I want to give like a little look into the data that end up going into the actual Synth function. So our time variable is year, and then our unit variable is city, and so that would be like the place ID. So it's called place because we're using census data. And then the input data have to be unique. The rows have to be unique at the time variable and the unit variable. So we have 13 years of data and 127 cities. So the number of rows should be 13 times 127. We cannot have missing values. At least we cannot have missing values for the outcomes of interest. And then we talked about predictors. So here I have all those 4 predictors here also go into the function later. But before, sorry, it got cut off a little. It was fine when I looked at it this morning, so I apologize. But before running SEM on this, we want to put the data from like a regular data frame into the data prep object. So data prep function is from the Synth package, and so what we did here is giving it the data. So that input data is what we just saw, and then the column names for the predictors, column names for the dependent variable. So that's the outcome. Column names for the unit and time variables. The special predictors are the lag values that we talked about earlier. And then it's like below here, if you could see it, so like you give it like the pre-treatment period that you want the algorithm to optimize, to use for the optimization. And then also it's like the ID for like the control and for the treatment unit and the control units. And from that, it's one line of code really. So you just run it through Synth and it does all of the magic and then gives you what you see here, which is another line of code to show you how the model, how SEM fits with your data. Out of the box charts are nice, but sometimes they don't give you what you want. So for example, here, I mean, it's like if you're working in base R, right, like you can add stuff to this, but who works in base R? We all love ggplot. So that's what we do. With a little bit additional code, like you can, I use data.table, and I'm realizing that a lot of people are tables people, but this is data.table syntax. But I love the ggplot tool package. So you know, extract the weights and then like try, and then we can put it into, this is not that great, but better than the out of the box chart. And then here's just a little bit of code again in data.table syntax, calculating the p-value using the methodology that I mentioned earlier, or described earlier. And yeah, and then once we have the right, like the series, we can visualize it, and then we have the p-value to let us know whether or not there's actually whether or not the difference we see between the counterfactual and the actual outcome is statistically significant. Now we are ready to communicate that to our stakeholders, and of course, I'm very, very happy to go after Molly because we have a Shiny app. So we put everything into Shiny app. This is actually public, and we have been updating it regularly as data come in. And yeah, and so this is our final product that lives on our website. So now you might be asking, what is the effect of the plan? I have not talked about that at all. So the plan went into effect in 2020. You know, a lot happened, right? Census data was a mess. Like So a lot of things happen, and it's still only 2022. So we don't actually have a lot of data to really sufficiently estimate the treatment effect yet. But we kind of see this, like we wanted to make this public because it's a way to monitor how things change over time. Not just the 10 indicators, we also have like additional contextual information that our stakeholders are interested in. And then it's a way for us to pre-register our methodology so that when we do have the data, we're not engineering it so that it fits the outcome that we want to see. Last slide. And then, so this is just the link, and the third one is the technical appendix that I mentioned. So all of the math that you want to see. And then here's that's the link to the slide. It's live on RPOPs. And with that, thank you, and talk to me if you have any questions.